Sean todos muy bienvenidos al Seminario Departamental que tenemos aquí cada martes en el CICATA Querétaro del Instituto Politécnico Nacional. El día de hoy tenemos una maravillosa plática preparada para ustedes con nuestro gran amigo David Hillier. Déjenme, se los presento para pasar inmediatamente a su plática. Entonces, David es radiólogo con especialidad en medicina nuclear y él trabaja para Kaiser Permanente, allá en Seattle, Washington, desde donde se comunica con nosotros. Él es asesor médico del programa de capacitación de tecnólogos en medicina nuclear del Bellevue College en Washington, Estados Unidos. En su educación, David realizó su pasantía en medicina interna, una residencia en radiología y una especialización en medicina nuclear por la Universidad de Washington en San Luis, Missouri, en Estados Unidos. También por la Universidad de Washington en San Luis. Obtuvo su doctorado en medicina y otro doctorado en medicina, en ingeniería eléctrica. Al tiempo, pues, antes de sus doctorados, obtuvo una licenciatura en biología y otra en ingeniería por el Swarthmore College en Pensilvania. Entre sus intereses, más allá de la medicina, se encuentra la radioafición, la electrónica, la carpintería, la fotografía y el fútbol. David, thank you so much for sharing this time with us, and I give you the voice. Go ahead now.
Okay, well, muchas gracias, Joaquin. I really appreciate the invitation. I'm sorry my Spanish is not so good, so I will give the talk in English. My apologies, but muchas gracias para escuchar en inglés. So let's get started. Let's see. Are you okay?
You should be able to share.
There we go.
Yeah.
Okay. So. Okay, so here's my talk about radio. But before I get started on radio, I just wanted to share a few things about Seattle, Washington, where I live, and my family, just real quickly. So I live in Seattle. Seattle is, of course, famous for the Space Needle, which was built in 1962 for the World's Fair. We have lots of mountains and lakes and things. Starbucks coffee, you know, muy importante. Alaska Airlines, Microsoft, public market is very popular. Costco, Boeing airplanes. So these are all things from Seattle. And now I'd like to introduce you to my family. So this is me with my wife and 4 wonderful daughters. Joaquin knows Adeline very well. Adeline is the reason that I traveled there and got to meet you all. Adeline, in July 2019, came to work at CICATA with Joaquin and Daniela, and I visited for 1 week, which was wonderful. So I'm surrounded by a wife and 4 wonderful daughters and a female dog. So I am outnumbered. So it is nice to have a brother. Mi hermano Juan comes to visit every weekend. We play soccer in sábado y domingo. And it's wonderful to have a brother because we can watch TV together. And that's how I got to see Game of Thrones and various TV shows. So everybody should have a brother to watch TV with. However, I will say that after a long week of work, that I can't actually tell you anything about Game of Thrones because this is what we look like watching television. That's my life, you know. And then real quickly, mom and dad. Joaquin knows of my father, so that was a nice connection. We talked about I was born at Stanford Hospital, as were 1 or 2 of your children.
Well,
yeah. It's interesting. So in 2019, I got to visit at CICATA, which was absolutely wonderful. Got a wonderful tour of this radiology manufacturing plant. It was extremely interesting. I really appreciated the tour. So thank you again for that. Loved Querétaro. It's beautiful. I was really taken with the aqueduct. We took a trip to Sierra Gorda, group photo. It was really a lot of fun. So with that, let's talk about radio. And so I've been fascinated with radio ever since I was a boy, even maybe 5 or 6 years old. I found it interesting, and it's easy to just become familiar and to forget just what a profound influence this has had. But if you can imagine a time before radio, or before the telegraph, or before the telephone, long distance communication was really a problem. Sometimes people would use smoke signals. You could use mirrors. They used runners. The term marathon is from, I think it's 409 BC. Phidippides, a runner, took a message from Marathon to Athens, Greece, over some 26 miles, and that's where the term marathon comes from. In Los Estados Unidos, we had something called the Pony Express, where a rider would carry mail for 10 miles, change ponies, and go another 10 miles, and just keep going like that to take a message across the country. Ships across the ocean, it could take 2 months to cross the Atlantic Ocean. You could write a letter to a family member back home, and it might be 2 seasons later before you would hear back. That has all changed now with radio. So it's good to think about this and what a profound impact this has had. So let's talk about the physics of radio briefly. When any charged particle is accelerated, a radio wave is produced. So a still charge does make an electric field, but does not make an electromagnetic field or a radio wave. A charge in motion also does not make a radio wave. If it is moving at a constant velocity, it has to be accelerating. And I saw a very good lecture explaining this. Essentially what is happening is you introduce a kink in the electric field during the time of acceleration. So if you imagine this particle is moving and beginning at a time, the electric field has propagated out this way. At this point in time, the particle was accelerating. At this point in time, it stopped accelerating. So the E field bent right there. And if you do the trigonometry, that results in a tangential component that is the radio wave. It turns out that this component varies in strength as 1 over the radius, not 1 over radius squared, not 1 over r cubed, just 1 over r. And that is very important. If it wasn't for that, this wouldn't work. This explains why radio waves propagate such a long distance. So that's the electric field, varies as 1 over r. The power density varies as the familiar inverse square law is, 1 over r squared, but the electric field itself only varies as 1 over r. And if you notice here, in the axis of movement, there is no kink. So there is no radio wave going straight ahead or straight back. And that should be familiar to anybody who does radio. If you imagine this is an antenna with charged particles moving back and forth, the radio wave propagates outwards. It does not propagate up or down, and this is why. You may have seen pictures like this showing the electromagnetic wave. I remember seeing a picture like this when I was a kid, maybe 10 years old or something, and thinking, well, okay, that's interesting. That explains what they mean when they say the electric field, if it's oriented this way, the magnetic field is perpendicular, but good grief, how does that form? You know, how does that make sense? Why does it look like this? Well, an easy way to understand this, or at least to conceptualize it, is to watch what happens in an antenna. So if you picture an amplitude modulated transmitting antenna, like with AM radio, it consists of a 1/4 wavelength monopole antenna. There'll be radials under the ground, typically buried maybe 20 centimeters under the ground. One end of your radio connects to the radials, the other one connects to the antenna, and you send current up and down the antenna. So let's watch what happens. Whenever the current is going up, well, it will go up. It's an alternating current, so it'll go up and then it'll go down, okay? To understand what happens with the magnetic field, remember the right-hand thumb rule. So if the current is going in the direction of my thumb, the magnetic field is in the direction of my fingers. So like this. And then when the current changes direction, it goes the other way. Okay, so let's follow that. When there's no current, there's no magnetic field. Now we have a weak current and a weak magnetic field. So the magnetic field is oriented this way in a circle, but is propagating out this way at the speed of light. Okay, then it gets stronger and stronger as the current gets stronger. And so it goes like this, and then it gets weaker, weaker, goes to 0, and then it changes direction. Okay, so there's your magnetic field. That intuitively makes sense. What about the electric field? Well, what causes the current to flow to begin with? You have to have a voltage, and to have a voltage, you have to have a charge distribution, and therefore an electric field. And look at the orientation of the electric field is parallel with the antenna. Okay, so, and then it does the same thing, it goes back and forth. So now we put the two together and we can see how you get a magnetic field and electric field, and they are perpendicular. So once I realized this, I thought, oh, okay, now it makes more sense. Now there's a problem, and you know, what frequency do you use to transmit? You know, why can't you just transmit the audio frequency that you begin with? Well, there are a couple of problems with that. There would only be one channel everybody in the entire world could use. And also at such low frequencies, the wavelength would be very long. It'd be about 300 kilometers. And so you would need a 75-kilometer tall antenna. You know, it's just not practical. So what we do is we use a carrier wave to carry the signal, which is at a much higher frequency. The receiving radio uses a tuned circuit to pick out the carrier wave from all the other radio signals using resonance. We place the information that we want to transmit onto the carrier wave using something called modulation. Okay, well, to understand this, let's first look at resonance. So a spring in a mass system naturally resonates. Okay, you can picture this if you draw the spring and the mass and the piece of paper. Okay, so I'm going to show you. Let's see here. Yeah. So here's
putting a pen in the
mass.
pen holder that's connected to the mass.
This is actually my daughter Merida's science project. And we get a nice sine wave. And if you change the springs, so now we put 3 springs on there instead of 1 spring on each side, it'll go faster. And so you get a higher frequency. So you can change either the mass or the spring and change the frequency. Okay. So we're, familiar with that. Okay, and let's just pause that. Okay, so it turns out using tuning forks is very helpful to conceptualize a lot of things that happen in radio. A tuning fork is simply a mass spring system. You can picture the spring as, the base of the tuning fork, and you have masses on the arms. Now, an interesting phenomenon that occurs with any resonant system is that it can easily transfer energy back and forth. So if we hit the tuning fork here, the energy will transfer to the tuning fork here, and it can actually go back and forth. So let's demonstrate that. This is kind of fun. Okay, first of all, so that's just the plain tuning fork. And can you all hear the tuning fork? Good, okay. Yeah, it's not coming in my ear, but as long as you can hear it. Now, if we add weights to one of the tuning forks, its frequency changes. And it no longer transfers energy. So okay. So you can see how energy transfers back and forth, and you can see how tuning is important. So let's look at an example then where you have multiple tuning forks tuned to different frequencies. Okay, so you can see this tuning fork and this tuning fork are the same frequency. These two are not. Well, that's very similar to what your radio is doing. It's just the same exact idea. So it is as though this, if you think of this as a radio and this as a radio, they're communicating with each other. Okay.
So we're going to start by demonstrating.
Okay, so let's keep going. So in electronics, the equivalent circuit is an inductor capacitor circuit, or LC circuit. It behaves in a very similar fashion. You can picture the capacitor as being like the springs. When you pull back on the springs, you're imparting potential energy to the system. Well, in this case, you just connect a battery to the capacitor, charge it up, turn this off, and then connect it through the inductor, and you pass the energy that's stored in the electric field in the capacitor to a magnetic field in the inductor. So that's similar to the springs giving energy to the mass in the form of kinetic energy, and then back again to the springs, back and forth. Okay. And so that on this box on the right is just an oscilloscope, so we can follow the voltage that results. Okay, so you see some of the charge is gone, but the energy is now forming in a magnetic field. Okay, and because there's less charge on the capacitor, the voltage is dropping, and eventually the charge is completely gone. There's no more voltage, but there's a strong magnetic field. So the magnetic field adds current back to the system and charges the capacitor in the other direction and back and forth. And you end up with a sine wave, just in the same manner as with the mass spring. So this is another one of Meredith's projects.
So we're going to start by demonstrating a sine wave with 4 microfarads of capacitance.
Capacitors here. And you get a sine
And as
wave.
you can see, it has a relatively high frequency. Now we're going to demonstrate a sine wave with 20 microfarads of capacitance. And this has a lower frequency. And now a sine wave with 100 microfarads of capacitance.
Because there is resistance, just like there is friction with the mass spring.
With an even lower frequency.
Oops. Did you get 8 set up to go? Thank you. Okay, and back to here. Now, one of the amazing things about radios is how strongly they can tune with clever design with multiple filters. It's amazing to me how precise you can tune in a particular channel. So a typical channel spacing in the 450 megahertz band is only 25 kilohertz. That works out to 0.006%. That is a tiny change between two channels. But the ability to do that electronically allows us to have many, many channels. So it's really, truly remarkable. Okay, so let's talk about modulation. Modulation is referring to what you do to a carrier wave to add information to it. And so let's talk about that. The simplest is what we call on-off keying, such as Morse code, you know, ... dash dot. Let's talk about amplitude modulation here. So an amplitude modulated wave consists of a carrier wave that you can see alternating very quickly here with amplitude modified according to the modulation. Okay, but now, how does that translate into the frequencies? So what happens to the carrier wave? It's no longer just a single frequency the way it started out. So let's talk about the frequency domain. And by domain, I mean the x-axis. So you can represent a sine wave in the time domain like this, like we're used to. But you can also simply describe a sine wave as consisting of a particular frequency, because we know it's a sine wave, so it's got a frequency and an amplitude. So you can describe it this way or this way. You can also give phase information, but we often don't care so much about the phase. Okay. So with amplitude modulation, you end up with a carrier and 2 sidebands. Okay, as shown here. But what are these sidebands? Okay, for years, I was confused about this. What are those sidebands? Okay, well, the upper sideband is simply the baseband signal. In other words, your original modulation signal, like coming from your microphone. Okay, that's the upper sideband, and it's just moved up in frequency so that it is just above the carrier, like we see. Well, I'll show you on the next slide. The lower sideband is the inverse of that. It's as though you're taking it and flipping it and putting it below the carrier. And this is easiest to demonstrate with simply a tone for the modulating signal. So a very simple signal. Okay, and I'm going to show this on the same frequency spectrum. So I don't want to confuse people with this. I'm showing the baseband signal here. Okay, so that's the signal that you get from like me talking into a microphone. That's different from the signal that's coming out from the radio. Okay, that's the radio frequency or RF signal. So that's shown here. This is the baseband signal. This is the radio signal. They're not the same. Okay, but it's convenient to show them on the same plot because you can see the relationships nicely. So this 1 kilohertz spacing from 0 to 1 kilohertz, it's exactly the same spacing between the carrier and the upper sideband and from the carrier to the lower sideband. Okay, so in the next demonstration, you're going to see several things. I hooked up a speaker so you can watch the speaker moving as we start out very slowly and increase the frequency. Once it's going very fast, you can't see the speaker moving anymore. You'll also be able to hear it, so you can hear what's happening with the modulating signal at the same time as you're watching what's happening here in the RF signal. And then this is the time domain representation of the radio frequency signal. So this is the modulation, the envelope is this. Okay, so let's watch that. Okay, first we'll watch it with the tuning fork. You see the baseband signal at the bottom there. Okay. Okay, and now for the AM signal. Okay, so if you watch, the speaker is moving very slowly back and forth. This is only 1/2 hertz, so you can see it. Okay, and you can't really see the baseband signal yet. It's too low a frequency, and you can't distinguish the sidebands yet. But you can see the speaker going faster and faster as I'm increasing the frequency. You can't hear it yet because it's below our threshold for hearing, but you will soon. We're up to 14 hertz, 15 hertz. Okay. Okay, 20 hertz. So pretty soon you'll start to be able to hear the tone. I'm just adjusting the oscilloscope and whatnot so we can see better. Okay, and now watch for sidebands down here at the bottom. You should start to see them appear. Now, as we increase the frequency of the modulation, look at those sidebands. Okay, as the frequency goes up, the sidebands are marching outwards. Okay, and in the upper right corner, you see that amplitude modulated wave and so on. Okay, so okay, let's move on. Okay, now in reality, we don't listen to tones very much. Life would be pretty boring in that case. So I created, or I should say Adeline created and I recorded a musical tone from her cello. She played a D note. And just, maybe 2 days ago, I realized when I looked it up that the D note is at 170 hertz, or no, 147 hertz, and hers was exactly at that same frequency. It was kind of funny. Anyway, so when you have a stringed instrument, and this applies to a lot of things, vocal cords or things, things that vibrate, you'll get a fundamental frequency when the string is vibrating like this. You get exactly twice the frequency at the second harmonic. You have the same spring constant all the way through, but only half the mass here, half the mass. This vibrates twice as fast as this one does. And then here, the third harmonic vibrates 3 times as fast, and so on. And so when she plays the cello, I recorded it, looked at it, took the spectrum analyzer, figured out how strong the components were, and then just recorded that so that it is now on a waveform generator, so I can use that as a test tone. So this is what it looks like in real time. This is what the various harmonics look like, fundamental plus the harmonics all added together give you this. Here it is again in the actual frequency spectrum. Okay. Now, if you want to demodulate an amplitude modulated wave, all you got to do is cut the signal in half by using a diode. It's very simple. And here's your load, a resistor. And if you want to smooth it, you can put a capacitor in there. So as the carrier charges the capacitor on the positive half cycle, it then only slowly discharges through the load and you get a smoothed signal. And so this next demonstration is going to be showing Adeline's D cello note with the frequency spectrum just like before. So here's the baseband signal on the left, the radio frequency signal on the right, and then this is the time domain radio frequency signal. Here it is cut in half with the diode, and here it is cut in half and filtered with a capacitor. So this is what your AM radio does. Okay, so let's look at that. And you hear the sound sounds vaguely like a cello. It's missing some harmonics. So I'm changing the amplitude. You can see how the sidebands are getting larger and smaller, and the depth of modulation is changing, and they're over-modulating. So you see how the sidebands get to be too big because we're over-modulating there for a moment. Okay. So here's a thing that I never understood for years, and I want to share with you how this actually works. So to get back to why do you get two sidebands like this that are just mirror images of the baseband signal? How does this added to this, how does that give you this? Okay, I never understood that for a long time until I actually created a lower sideband, a carrier wave, and an upper sideband with 3 different waveform generators myself, added it together and looked at what happened. And then it made sense. So I'm going to share that with you. But first, I'll just show you the math works out. Here's your carrier wave, okay? Just a sine wave at a carrier frequency times time, times 2 pi. You have to convert from radians at some amplitude. And then you have your modulating frequency here. And you have to add 1, and actually the M should go away. It should just be cosine. Add 1. You have to add 1 because otherwise you'll be multiplying your carrier by a positive number, then a negative number, then a positive number, then a negative number as the modulation changes. And that's not what you want. You'll end up flipping the phase and it won't turn out right. You have to add 1 so that this varies between 0 and 2, this term. Okay, so that's logical, but it's crucial because this 1 is where you're getting the carrier term from. That's why in amplitude modulated waves you have a carrier in the middle. And then when you multiply a cosine times a sine, you end up, but there's a trigonometric identity where you end up with the sum and the difference frequencies. Okay, well, okay, that's nice. This works mathematically. You have a carrier and you have 2 sidebands, but still, it's hard to conceptualize. So to understand this, let's talk about beating. So beating is a phenomenon that occurs when you add two sine waves together. This is a sine wave, I think it's 200 hertz and this 240 hertz added together, and you get the sum that results is a sine wave that varies in amplitude depending on whether these are in phase, and so you have a strong signal, or they're out of phase and you get a weak signal. So it alternates strong to weak, okay? So that's a phenomenon that's important to understand what's happening with amplitude modulation. See, Meredith, what happened to the video there? So we're on 12. Okay, so these are two tuning forks beating. Switch one. Oh, sorry. Let's do that again. Okay, two tuning forks at slightly different frequencies. Okay, and you see how they beat against each other very slowly. Now, if I move the weights up, that's going to change the frequency more. So we're going to beat faster. And then as I move the weights even further up, they beat even faster. Now, you may have heard something like this on an airplane. Airplane engines turn somewhere around 10,000 to 25,000 revolutions per minute. So say in the ballpark of 200 hertz. If the engines are not turning at the same speed, at the same rate, they'll beat against each other. So have you ever been in an airplane where you hear this phenomenon? Okay, so right now they are at the same frequency, but I'm going to change that and watch the frequency here. I'm going to change it to half a hertz above 200, and you're going to hear a whoa, whoa kind of sound, okay? Second here. So now they're beating at 1 hertz. Goes faster and faster. Okay. Get 14 ready to go. Thank you. Okay, so that's beating. So now I'm going to explain to you how amplitude modulation actually works. And when I first realized this, maybe 5 or 6 years ago, I was rather excited. I'm easily excited by such things. Okay, so here I created a carrier wave with a waveform generator, which we can see here on the fast Fourier transform here. Here is an upper sideband, so it's at a higher frequency. And there was a lower sideband as well. I didn't show you, but that's this one. This is the FFT, the fast Fourier transform of the three together. This is the resulting waveform, okay? Well, let's look what's going on. So right here, you can see the resulting waveform is very strong. all three waves are in phase, okay? The two carrier waves are in phase, and they're in phase with the, the two sidebands are in phase, and they are in phase with the carrier. Well, these sidebands are twice as far apart from each other as they are from the carrier. So they beat against each other exactly twice as fast. So the next time the two sidebands are in phase is right here. See that? But they are exactly out of phase with the carrier. And so you get a small signal. And then when they're in phase again here, well, now they're back in phase with the carrier. So that's why you need all three. It wouldn't work if you have, multiple sideband frequency components. They wouldn't all add together properly if they weren't also beating against the carrier. So kind of a neat, thing to understand. And now, understanding that logic, you can see that it's important that the amplitudes of all of these sideband frequency components added together and all of these added together have to be less than the amplitude of the carrier, or you'll overmodulate. It won't work anymore. And so what do I mean by overmodulation? Okay, well here I'm going to show you 0% modulation. Okay, so that's like a quiet moment during a broadcast. There are no sidebands, just the carrier. Okay, just the carrier. A little bit of modulation. Okay, it's 10%. You have small carriers. Okay, so let's keep going. See the carrier, the sidebands are getting bigger and bigger. Look at the modulation, it's getting pretty big. Okay, it will get to 100% modulation when the two sidebands are exactly half of the carrier. So let's watch that. 100%, exactly half. You go beyond that and oops, okay, this is no longer right. Your modulation did not look like this. So that's overmodulation, and it results in distortion. As you can see here, there's some extra components in the frequency spectrum that don't belong there. So you don't want to do that. Now, the whole point of having amplitude modulation is that it's very simple. It's easy to construct a radio to do amplitude modulation, to transmit it, but it's also very easy to receive it. All you need to do is cut the signal in half with that envelope detector that I showed you before. And that's why we started with this. Okay, well that's fine, but it's wasteful. Most of your energy is in the carrier, or a lot of it is certainly in the carrier. I think it's most. I have to do the math again. I think that's right. And you got the information in the upper sideband is the same as the information in the lower sideband. It's duplicated. So you're using twice as much frequency spectrum as you would need to. And this carrier really doesn't give any information. It simply makes it easy to demodulate the signal. So what you can do is get rid of the carrier, get rid of one of the sidebands, and only transmit one sideband. That's much harder to detect. You have to multiply the resulting signal by another sine wave to do something called heterodyning, where you bring the frequency back down to baseband to hear it. And that's trickier, but certainly possible. And that's called single sideband. And this is an example from a real radio, where this would be an example of just Morse code, continuous wave or Morse code. This is amplitude modulation like we just looked at, and this is the cello D note we've been watching with the two sidebands, but most of the energy in the carrier. Here's upper sideband, no carrier. The carrier would be right here. It's only 3 kilohertz wide instead of 6 kilohertz wide, and all of the energy is going into sideband where the information is. And then there's FM, and FM uses a lot more spectrum. As you can see here, it's about 16 kilohertz wide. So that's a disadvantage of FM. Okay, and so I'm going to show you frequency modulation in action. And I wish I had more time to talk about modulation, but that's going to be my last demo for modulation. Then I'm going to show you one last really interesting thing to me, showing the sensitivity of radio. So I'm coming to near the end, but I'd be happy to talk more about modulation if people have questions. So in this demonstration, we'll see the speaker again like before, and we're going to increase the frequency, and we're going to watch what happens. So here's the modulating signal, okay, and the radio frequency signal. You can see how the spacing here gets bigger. This is frequency modulation, and it's more narrow here, okay? So the frequency is being changed, not the amplitude. Here's the baseband signal. Here it's shown again, but this is the radio frequency wave that results. And you can see how broad it is. It consumes a lot of bandwidth, but it's more resistant to noise than either AM or single sideband. It has some big advantages. So let's play that. Okay, so the first thing you're going to notice is this is only 1/10 of a hertz modulation. Okay, this modulating signal is very slow, so that we can see the frequency of the carrier wave changing, and then look at the frequency of the carrier wave is just going back and forth, back and forth. That's frequency modulation. Okay, we're going faster. This one has a 2 kilohertz deviation. So that's the distance that the carrier wave is going back and forth here, 2 kilohertz. And that's your FM frequency spectrum. Start to hear it now. So FM is confusing. It's not an image of the original baseband signal at all, as you can see. It's hard to understand. Okay. And okay, we'll get to this last couple of videos in a second here. Whoops. Oh, that's a JPEG. Hey, Meredith, could you find the next video there? Thank you. It should be number 98. Thank you for your help. Okay. So the last thing I'm going to talk about, and this won't take too long, is the remarkable sensitivity of radios. They're very, very sensitive. They have an extreme dynamic range. It's, you know, in the range of 12 orders of magnitude between the power at the highest that the radio can receive without, you know, being overwhelmed, and the lowest power. And this allows for such things as communication with deep space probes, for example. Typical sensitivity in your radio is around 16 microvolts. That's tiny. You can't even see that on your oscilloscope. I mean, it's really, really tiny. It's equivalent to negative 123 dB with respect to a milliwatt. So when I refer to sensitivity, it's really not so much the sensitivity as low noise. You can introduce an arbitrary amount of amplification in any signal, but eventually you're going to run up against noise. And so, you know, this amplification will continue to work as long as you have a good signal to noise ratio. Okay, so if your signal looks like this and the noise looks like this, well, that's fine. But if it's like this, you're not going to hear it anymore. So in amateur radio or radio aficionado, which I do, one thing that people will do is communicate via satellites. So this is an example, this SO-50, Saudi Oscar 50. So this was actually built in Saudi Arabia. It's a little tiny satellite. It's only, literally, it's this big. It's a CubeSat. It's maybe 30 centimeters on the side. 600 kilometers high in orbit. It has a downlink. So let's see, I got that backwards. Yeah, the downlink is in the 70 centimeter band. The uplink is in the 2 meter band, but you know, so it receives and transmits on 2 different frequencies. It uses these monopole antennas. They're not directional. It's not a big parabolic dish or anything. And it transmits with only 1/4 watt of power. And that is extraordinary, that you can do that and still it works. So this functions as a repeater in space. In other words, you transmit to it, it takes your signal and retransmits it down on the downlink so somebody else can hear it. And then they transmit on the uplink and back down again so you can hear it. Okay, so it just functions as a repeater, but it's transmitting with 1/4 watt of power. Okay, that is equivalent to the power in this Christmas tree light. I actually had a hard time finding a light bulb with this little amount of power. So it's transmitting with that much power, but you can still hear it. And so 98, is that a video? Yes. Oh, okay. Well, we'll listen to this one. We'll switch gears. So that's Adeline and the whole family got involved. Maybe turn up the volume so people can
M7OM, is it? WI7P.
Yeah, WI7P.
November 90, California.
Charlie Mike 97.
Yeah.
N7OM, this is
N7OM.
November Whiskey Sierra, Charlie November 87. NWS, this is Whiskey India 7, Papa.
Whiskey 07 Papa.
WI7.
Whiskey 07 Papa.
I got the hotel. November, Juliet 7 Hotel, NJ78.
Okay. So that, I think, is extraordinary. I can't really even fathom how that works. So one time, Adeline made a contact with somebody via this satellite. So based on the angle, it's 600 kilometers high. It was probably 1,000 kilometers away as she's transmitting to it. Okay. And so you might think, well, boy, you know, she could talk to somebody, you know, another, you know, maybe 1,000 or even up to 2,000 kilometers away, say, depending on the angle. That would be pretty neat. Turns out the person she made the contact with was also in Seattle. So she went to the trouble of transmitting 1,000 kilometers. The satellite transmitted 1,000 kilometers back again. And it turns out the person she was talking to was 12 kilometers away. We could have walked there in 2 or 3 hours. But, you know, Adeline always has been an overachiever after all. why do it simply? You know, why use the telephone? You can do it more dramatically, right? Now you can do even more amazing things if you take time to average the signal over time. The noise will tend towards zero as you average it, whereas the signal will get stronger. So using slow communication, radios can receive even weaker signals. GPS signal to noise ratio is actually negative. And I tried looking it up before this talk. I had trouble finding it. I want to say it's around -20 or -25 decibels, which is why GPS receivers are so slow. You know, they need time to pick out the signal. Deep space probes do this all the time. They're, of course, using big, you know, parabolic dishes, especially on the ground, but even the probe has a parabolic dish. And they do it very, very slowly. So, you know, you can talk, you know, with Voyager out beyond the orbit of Pluto. It's incredible. It's really, really incredible when you think about this. So those are a few of my favorite things about radio. I hope you enjoyed it. Muchas gracias. Thank you so much for inviting me.
Thank you, Dave. Thank you. Now we
You're
have
welcome.
a few questions here. They are in the chat. Let me try to read them. So Jose Armando Olvera is asking, why radio signals has no suffer analog switch off?
No switch off?
Uh-huh.
See, I don't understand.
Neither do I. Jose Armando, could you please elaborate? So a few years ago, we were switching from analog to digital in TV.
Ah,
So that,
okay. Yes, I remember that. I was fascinated by it. In fact, analog television, even though it's quite old technology now, was really remarkable in its time. And I was at work and I took a little video of the switchover. I was fascinated. Just they turned it off and put the digital signal on right away at exactly the time they said it was. There are some fancy things you can do with digital technology, error correction, and various things that we can't do with analog. I was hoping maybe there would be time to talk about 5G telephone. That's really fancy. I'm still trying to learn about it myself, but they use multiple carriers and they use signals that don't interfere with each other, multiple signals at the same time. They're referred to as orthogonal, so there are some neat tricks you can do with digital. But even with the old analog, I think that my favorite lecture I ever heard as a college student was given on the old TV. And the things they figured out then with vacuum tube technology were phenomenal. So I'll give you just my favorite one. So you may remember back, I don't know if it was the 1950s or so, television was black and white. And it had a 6 megahertz bandwidth. And then they realized, well, now we could do color. But what are you going to do? You've used the entire bandwidth. What do you do? Well, if you think about it, the scan, the raster scan for the TV goes from line 1 to 3 to 5 to 7, and it comes back and does 2, 4, 6, 8. One line to the next line, the two are very similar. The picture doesn't change much when you go across from one line to the next. So what you get is not completely, but a lot of what seem like repeating signals. Okay. It turns out in the frequency domain, if you have 525 lines that you scan, you end up with 525 frequency spectra. So kind of like this. Well, that's your black and white signal. The color does the same thing. So what they did is they took the color and they just shifted it right in between the black and white. They just shifted it over slightly, and they made it less strong so it wouldn't interfere with black and white TVs. They only transmitted 2/3 of the color information because the black and white signal already has the full luminance signal. So anyway, it's my favorite example of a very clever thing they did with the old analog technology, developed in the 1930s. It's amazing to me.
So David, let me try to rephrase Jose Armando and maybe second guess what he has in mind. So more and more we live in a world with digital devices. We use cell phones and we communicate through WhatsApp. Why do you think it is still relevant radio communication?
Ah, yeah, okay. Well, a lot of it is still radio. Your cell phone is a radio. It's a very fancy radio. So radio technology is still used all the time. Now, some things like the old AM broadcasts are not, people don't listen to as much anymore, for example. But we still use radio technology all over the place. Also, old style radio is very useful in emergencies. So, for example, Hurricane Maria in Puerto Rico, the infrastructure was heavily damaged. Cell phone towers, most of them didn't work anymore. Even if the tower is standing, it still needs its landline connection to work. And a lot of that was gone. But if you have a radio and say a 12-volt car battery and an antenna, you're good to go. You can communicate. And so the amateur radio is extremely useful in emergencies. So that's one thing. I mean, it's a fun hobby, but by doing it, by playing with it all the time, then you get good at it. And so when there is a disaster, that's when we come into our own. We come out of the woodwork, so to speak, and we help. So there are still quite a number of reasons to continue doing the old style radio.
All right. Well, David, I think that we ran out of time. I would like to acknowledge and to thank you for preparing this wonderful talk that took us from the simplest things to the more complex ones, from amplitude modulation to frequency modulation, from physical experimentation to experimentation with waves, from physical to electronics. Thank you very much for your talk. I enjoy it a lot, and thanks for the inspiration that you give us through your talks. Thank you very much.
Well, you're quite welcome, and thank you so much for inviting me and for being my friend. This has been a lot of fun.
Perfect. Thank you very much. Well, here we prepare a small diploma. I will send it to you as a demonstration of our thankfulness for your talk. Thank you very much.
Well, thank you.
Y ahora pues nos toca despedirnos por el día de hoy. Les recuerdo que todavía tenemos una sesión más el siguiente martes y pues los esperamos aquí en el Seminario Departamental del CICATA Querétaro. Muchísimas gracias por su atención y que pasen una maravillosa tarde. Gracias. David.